Hi there. We looked at some basic associations and tests of differences in chapter 11. And right now what we're going to do is we're going to take a look at some covariation and variable relationships in chapter 12. Specifically correlation, bivariate regression, and multiple regression. So in correlation analysis, let's take a look at it and let's think about it a bit. The Pearson correlation coefficient is a measure of the strength of a linear relationship between two metric variables. The correlation measure is varied between -1 and +1, with 0 representing absolutely no association between two variables, and -1 and +1 representing a perfect linkage between two variables. The higher the correlation coefficient, the stronger the level of association. The correlation coefficient can be either negative or positive, depending upon the direction of the relationship between the two variables. The size of the coefficient can be used to quantifiably describe the strength of the association between the two variables. If it is a negative correlation, as one variable goes up, the other variable goes down. If it is a positive correlation, as one variable goes up, the other variable also commensurately rises. Now, there are basic assumptions about the types of data and rules of thumb regarding the Pearson correlation. The two variables are assumed to have been measured using interval or ratio scaled data. The nature of the relationship is assumed to be linear, and the variables come from bivariate, normally distributed populations. Now, if we look at the coefficient of determination, or the square of the correlation coefficient, it explains how much of the proportion of proportion of variation in one variable is accounted for by another. So, if you have a r² of 0.4, that means that 40% of the variance between the variables is explained. Now, if you have rank order data, you can still do a correlation, and you would use the Spearman rank order correlation. Now, the Spearman rank order correlations tend to produce smaller correlation coefficients and therefore are felt to be a more conservative test. In other words, it's more difficult to show high correlations between two variables, so it's conservative in that regard. You will see in your exercise that you have both Spearman and Pearson correlations that would be expected of you in this chapter. So if just looking at a basic association between two variables isn't sufficient for what you're doing in the analysis, then you can take a look at basic regression analysis. And in regression analysis, you're taking a look at the linear relationship between two variables in a straight line. And the basic formula for the straight line is y equals ax plus b, where y is the dependent variable, a is the intercept point. That's where the straight line intersects the axis when x is 0. B is the slope, or the change in y for every 1 unit change in x. And x is the dependent variable used to predict y. And then the e on the end is the error term for the prediction. And in regression, we're looking at the relationship between the x and the y variable, and the independent variable is the x variable, and the dependent variable is the y variable. So the question we're trying to address is, can the independent variables, that is the x variables, create or predict a change in the dependent variable? Now, we use the least squares approach to the best fitting method for regression analysis at this point. At least at this point in your statistical MBA career, we're going to be looking at ordinary least squares. And that estimates the regression coefficients that produce the lowest sum squared differences between the actual and the predicted values of the dependent variable. So when we get the output for the regression equation, what are the things that we're going to look at? Well, the first thing we're going to look at is the ANOVA table, and is the F value significant? And that would indicate that there is a predictive relationship among at least one of the independent variables and the dependent variable. Then we would look at the R square, which tells us how much of the variance in the dependent variable is explained by the independent variables together. And finally, we'll look at the betas and the standardized betas and the t-test for each of these betas. Now the t-tests tell us which of the betas are the significant predictors. So again, we're looking for a value less than 0.05. The betas are used for developing the linear function equation discussed earlier. The y hat equals. I provided that a little bit before. The standardized betas allow us to examine which of the variables actually is the strongest predictor of the dependent variable. So, again, the R squared determines or describes the strength of the relationship between all of the independent variables in the equation and the dependent variable, and how much of the variance in the dependent variable is explained. And the beta coefficients, the standardized beta coefficients, allow us to assess the relative influence, and the t-statistics of those betas allow us to determine which are significant predictors. Now that wraps up my basic summary for chapter 12. Good luck on your assignments, and if you need any help, please feel free to call your instructor.